In this video, we're going to take a look at problem number 2 from the Step Input to Second Order Systems in-class problem solving session. In this problem right here, we have a 4 amp supply that has been connected to this inductor L1 for a long period of time, and then it has not been connected to this resistor and this capacitor R1 and C1 because the switch has been open for a long period of time. R1, C1, and R2 have been connected to the 30-volt supply for a long period of time, and we're going to use all of that information to help us come up with the initial conditions for this system. At time equals 0, we're going to suddenly close switch 1 and open switch 2. So when we do that, we're going to disconnect this resistor R2 from the power supply, and we'll be left with a parallel RLC circuit that is in parallel with this constant 4 amp supply. And we're asked to model how the current through the inductor L1, this inductor right here, will change as a function of time after that switch change, the positions of the switches change. So what I've done here is I've drawn the two conditions, the before time equals 0 condition and the after time equals 0 condition. So this is the circuit that we're going to first of all develop the differential equation model for. We have an inductor and a capacitor in this circuit, so we know that we have two energy storage elements, therefore it must be modeled by a second order differential equation. Now we need to set about finding that second order differential equation that describes how the current through the inductor is going to change. Now, since we're looking for the current through the inductor, we may be inclined to initially use the mesh current method and to establish the current flowing through the inductor. I'm going to take an alternative approach because if we look at this, we would have 3 meshes in this circuit that we would have to deal with. And then we would have to couple all 3 of those meshes together, all 3 of those mesh equations together. However, if we look at it from a node voltage perspective, we have 2 nodes that we need to worry about and develop equations for. Of course, one of those nodes we're going to call the reference node. Therefore, we only need to develop one equation to solve for the voltage across all 3 elements, the inductor, the resistor, and the capacitor. And of course, we also know how to relate the voltage across an inductor to the current through the inductor. So therefore, if we start off using the node voltage method, solving for the output voltage across all 3 of the elements here, we can replace the voltage across the elements with a relationship that tells us about the current through the inductor. So what I'm going to do is I'm first going to apply Kirchhoff's current law using the node voltage method to this output voltage node here with respect to ground. Doing so, I know that all of the currents that leave the node must sum to 0. Since I have this current supply, this constant current supply I1 going into the node, that's going to be a negative value, negative I1. And then I need to worry about the current leaving through the inductor, plus the current through the resistor, plus the current through the capacitor. And all of that has to sum to 0. Okay. The current through the inductor is the variable that I'm trying to develop the differential equation in terms of. So therefore, I'm going to leave this one fixed, and I'm going to take I1 to the other side of the equation. Alright, so IL will remain, and then I'm going to write the current through the resistor and the current through the capacitor in terms of the node voltage at the Vout node. So the current through the resistor can be written as Vout minus our reference node, which is 0, divided by the resistance, plus the current that passes through the capacitor can be written in terms of voltage by the relationship of C times the derivative, the capacitance times the derivative of the output voltage across the capacitive element, which is Vout minus 0. I'm going to take my current, my input current, and bring it to the other side of the equation because that's going to become my forcing function. And I'm going to multiply this by the unit step function just to make sure and make it clear that this input function is not constant at I1 for the entire period of time. It only happens after time equals 0. So this is just some mathematical notation to remind me that this is not a constant value for all of time. Okay, now that I've done that, I'm going to get rid of my 0 values here, and I'm going to multiply through by the denominator right here, r, so that I can get rid of some of these fractions. Doing so will leave me with R1 times the current IL, that's a 1 right there, plus V out plus RC times dV out dt is equal to R times the current supplied by the current supply times the unit step function. Okay, so my differential equation now is taking form, but I still have a mixed form of the equation. I have both the output voltage as at this node as well as the current through the inductor, but I want to get all of my terms in my differential equation all in terms of the current through the inductor. But luckily we know the relationship between the voltage across the inductor and the current through the inductor, and that's given by the inductor relationship that the voltage across the inductor is going to be equal to L times the rate of change of current through the inductor. Okay, we also know that the voltage across the inductor is the same as the voltage across the resistor, and is the same as the voltage across the capacitor because all of these elements are in parallel with each other. Therefore, the voltage across the inductor is the same thing as the output voltage. So I'm going to take this relationship now and substitute it into this Kirchhoff's current law balance. Doing so will give me the following. R times the current through the inductor is the first term. I'm going to replace V out with the L di dt term. And to substitute into this equation, I'm going to have to take the derivative of this relationship, which will give me RLC times the second derivative of the current through the inductor with respect to time. Oops. And that must be equal to R times the current supplied by I1 times the unit step function. Okay, so doing a bit of rearranging here, put it into standard form. I have a second order differential equation in terms of the current through the inductor. Now that I have that, I can get my variables that are important for solving this differential equation. So this becomes my inertia term, this becomes my damping coefficient, and this becomes my stiffness term. On the right-hand side of the equation, after time equals 0, this is my forcing function. And my forcing function is equal to R times I. And eventually I will need to know the forcing function, the value of the forcing function, divided by the stiffness of the system, which will be Ri divided by K, or will be the F divided by K, which is Ri divided by R, which is the same thing as the input value I1. Okay, now from this, I can also calculate my damping ratio. So my damping ratio is defined as C over 2 times the square root of Km. C is L over 2 times the square root of K times M, gives me R squared LC. And doing some algebraic simplification on that, I wind up with 1 over 2R times the square root of L over C must be equal to the damping ratio. So now I'm going to calculate what that damping ratio is in order to determine whether the system is overdamped, critically damped, or underdamped. In addition to that, I'm going to calculate the natural frequency because I'm going to need that value to calculate the eigenvalues of the system. The natural frequency is given as the square root of K over M, or the stiffness divided by the inertia, which is the square root of R over RLC, which is the same thing as the square root of 1 over LC. Okay, so now I'm going to go to Excel so that I can do these calculations here. So I've already entered into Excel the values of the resistance, the capacitance, and the inductance. And now I'm going to use the relationship that I just established to calculate my damping ratio. So my damping ratio is given as 1 divided by 2 times the resistance multiplied by the square root of the inductance divided by the capacitance. Okay, and that gives me a value of 1.25, which means the system is overdamped. Okay. I can also calculate the natural frequency here, and the natural frequency here is going to be the square root of 1 divided by the product of L and C. Okay, and the natural frequency has units of radians per second. So that gives me 2.5 radians per second, and I know that the system is overdamped. Okay. Now that I know that the system is overdamped, I can go to my second order systems with forced input worksheet, and we can look for the overdamped system general equation. Okay, so I know that if the second order system is overdamped, and I can find the initial conditions, which is what we need to work on, that the general step input solution is going to be given by this equation right here. Okay, where some unknown constant times e to the first eigenvalue times time plus another unknown constant times e to the second eigenvalue times time plus the forcing value, the constant forcing value divided by the stiffness of the system. Okay, so now that we have that, we have to calculate the eigenvalues, and we also have to determine the values of these unknown constants a and b, which means we need to determine the initial conditions of the system. Okay, so to calculate the eigenvalues for this, I'm going to go back to my Excel sheet, and I know that the eigenvalues for an overdamped system are going to be calculated as follows. I'm going to take the opposite of the product of the damping ratio and the natural frequency, and first I'm going to add to that the square root, I'm going to add to that the product of the natural frequency times the square root of the damping ratio squared minus 1. Alright, and that gives me my first eigenvalue. The second eigenvalue is going to be identical to that, except the square root term here, we are going to subtract that square root term instead of adding it. Okay, so now I have my two eigenvalues, negative 1.25 and negative 5. So now I need to determine my initial conditions and my derivative initial conditions. Okay, so now to determine the initial conditions and the derivative initial conditions, I need to take a look at what's happening with the system before and after the event occurs. And then I need to use the relationships between how quickly the capacitor and the inductor voltage and current values can change. So before time equals 0, we have two separate systems because of the switches. We have one system where I1 is supplying the inductor, and our second system has two resistors in it, R1 and R2, and we have our capacitor right here, C1. And that circuit is connected to our voltage supply, V1. Okay, now that we know that, we also know that the current supply is 4 amps, and we know that the constant voltage supply is, what is that? The constant voltage supply is 30 volts. We also know that R1 and R2 are both 20 ohms. Okay, so now that we know that information, we're going to take a look at what we know, what this tells us. So before time t equals 0, we know that the system is operating in the DC steady state. And because it's operating in the DC steady state, this inductor behaves like a wire. If the inductor behaves like a wire, we also know that all of the current through the inductor before the event happens, right, before the switches change position, must be all of the current that's being provided by this current supply, which is 4 amps. Okay. So after time equals 0, we know that we have this parallel RLC circuit. So that's our inductor, our capacitor, and our resistor. Okay. We know that based on the properties of inductors, that the current through an inductor cannot change instantaneously. So if before time equals 0, there's 4 amps of current passing through the inductor, right after the switches change position and we form this new circuit, that means that the current through the inductor at time 0 plus the instant right after we close the switch must also be equal to 4 amps. Okay, so that provides us with our initial condition. Now we have to do a little bit more work to determine the derivative initial condition. So to determine the derivative initial condition, we're looking for the rate of change of current through the inductor as a function of time, right at time 0 plus. All right, right after the switches close. Now we need to think about what relationship we know that will tell us something about the rate of change of current. And we know that from the inductor relationships tell us that the voltage across the inductor is equal to L times the rate of change of current through the inductor. All right, so if we can determine the voltage across the inductor at time 0 plus, then we can solve for the rate of change of current through the inductor at time 0 plus. Okay, so we're going to try to solve for this. So now we need to set about determining what the voltage across the inductor is going to be. Now, the other thing that we need to note is that these elements are in parallel with each other. So if we can determine at time 0, right after the switch closes, what the voltage across the resistor and the capacitor are, that has to be the same by the fact that of the definition of parallel elements, that the voltage across the inductor is the same as that across the resistor and the capacitor. Also, we know something about how the voltage across a capacitor can change. Excuse me. We know that if we can determine the voltage across the capacitor before the event happens, we know that the voltage across the capacitor cannot change instantaneously. Therefore, the voltage across the capacitor has to be the same right after the switch changes as it was before the switch changed. Okay, so here, before time equals 0, if this has been operating in the DC steady state, we know that the capacitor acts like an open circuit. If the capacitor acts like an open circuit, there's no current passing through that capacitor. So all of the potential that's developed across this open circuit or this capacitive element will be the same as the potential that's developed across resistor R1 because R1 is in parallel with C1. Okay? We also know that resistor 2 and resistor 1 are of the same value, both 20 ohms. Okay? So we can determine what the voltage is across the capacitor at this node right here because we have a voltage divider between R1 and R2. Right? So we're going to find the initial voltage across the capacitor at time 0 minus is going to be given by our voltage divider equation, which is V1 times R1 over R1 plus R2, because we're trying to find the voltage across this resistor, which will in turn be the voltage developed across this capacitor. Since R1 and R2 are of the same value, we know that it's also going to be half of the input value. So that means the initial voltage across the capacitor at time 0 is equal to 15 volts. We also know that the voltage across the capacitor cannot change instantaneously. So right after we change the switch position, at time 0 plus, the voltage across the capacitor has to be 15 volts still. Since the capacitor is in parallel with the inductor, that means that the voltage across the inductor at time 0 plus, VL at time times 0 plus must also be 15 volts. So now that we know that, we can substitute that back in here. So we know that then we can solve for di dt through the inductor at time 0 plus must be equal to the voltage across the inductor divided by the inductance, which will be 15 volts divided by the inductance. Okay, so now that we have those two established, we know that the initial condition for the current is 4 amps, and we know that we can calculate the rate of change of current as being 15 volts divided by the inductance of the system. Okay, so coming back to our spreadsheet here, I know that my initial condition is 4 amps, and my derivative initial condition is going to be the 15 volts divided by the inductance, which is 20 henries. Okay, so 0.75 amps per second. The other thing that we need to establish is the forcing function divided by the stiffness, F over K. And we determined previously that that value would be the same as the constant current supply, I1, which is given as 4 amps. Now that we know all of that information, we have everything that we need to be able to calculate using these formulas right here for the overdamped system, the constant values A and B. So I'm going to use those relationships to determine the constant values A and B that are going to be given for our solution. So B right here is given as the derivative initial condition, V0, plus the first eigenvalue times F over K, or times the quantity of F over K minus the initial condition. All right, all of that is going to be divided by the difference between lambda 2 and lambda 1. So lambda 2 minus lambda 1. All right, that gives me the value of B. And the value of A is going to be the initial condition, x naught, minus B minus F over K. Okay, so from this I see that I have two conditions. I have my two constants, A and B, which will be used in my final solution here. All right, and then I have, and I also know the value of F over K, so our final solution is going to take this form right here. Okay, so I can also do some simplification on that. And if I do some simplification on that and look at the results, we have the same results that are given in the results spreadsheet, or excuse me, the result PDF here. And I can pull out that constant value of 0.2 because it's negative in front of one of the values and it's positive in front of the other exponential term. All right, so this is going to be doing a little bit of algebra on that. This will be the final solution right here. And then what I would like to do is I would like to take this solution and plot it so that we can see what the response behavior is going to look like. All right, so now what I've done is I've created a time column and my current, which I'm going to enter that result into. All right, so I'm going to take A times E raised to the lambda 1. All right, I need to make these absolute references. And then I'm going to multiply that by the time column. All right, and that does not need an absolute reference because the time column is going to change. Then I'm going to take B times E raised to the second eigenvalue times time plus F over K, absolute reference. Okay, so we see that at time 0 here, our current is 4 amps, which is true to the initial condition. All right, and then what I'm going to do is I'm going to try increments of 0.5 seconds, or half a second, and I'm going to then take this formula and fill out the rest of the columns, or drop it down to the rest of the column. So now I have on column B the evaluation of the function of time that describes how the current through the inductor changes. And in column A, I have the time column in seconds. So now I can insert a scatter plot that's going to show me the behavior of the system as a function of time. So we see from this that at time equals 0, the current is 4 amps. And then, right after the switch closes, because our derivative initial condition is a positive value of 0.75 amps per second, the current through the inductor is initially going to shoot up, and then it's going to reach some peak value, and it's going to then settle back out at a constant current of 4 amps, again, because that is our forcing function value. Now, we can make some sense of this again if we look at our derivation, and if we look at physically what's happening with the system. Okay, so if we go back to our to where we derived the conditions or derived the equations, we see that our inductor will be charged, or excuse me, will have a current flowing through it of 4 amps, and this capacitor right here will have an initial voltage across it of 15 volts. All right, so we determine those initial conditions, and then as soon as the switches change position, we have 15 volts across this entire circuit right here. Some of the charge that is stored in the capacitor is then going to discharge through the resistor. All right, and it takes some time for the current to change through this inductive element. So therefore, all of the current is going to have to pass through this resistor, and some of this current passing the additional load of this resistor is going to cause some of the current to be supplied by this current supply right here. So some of the current that's being dumped out of this tank will initially not be able to go through the inductor, but after a little bit of time, we're going to have since we have a larger potential across the inductor, we're going to get some increased flow of current through this inductive element. But after a long period of time, once this operates for a long period of time, the capacitor again is going to act like an open circuit and not allow any current to go through it. After a long period of time, the inductor is going to act like a wire, and all of the 4 amps that's being supplied by the 4 amp supply are going to flow through that inductor. So essentially, the capacitor is not going to matter anymore, and the resistor is not going to matter anymore after the switch has been closed for a long period of time, because the inductor is going to carry all of the current, again, that's being supplied by that current supply. So this initial bump up in current that we see is primarily due to the discharging of the capacitor. Okay, and that's the solution to the second problem of the worksheet.